Hi, Emmanuel here. Welcome again to another class. And in today's class, we're going to be talking about mathematical induction. Now, mathematical induction, by the way, is a mathematical method of proving that a given statement holds true for natural numbers in a series like this. Now, since natural numbers are infinite in number, this implies that for a limited number of cases, this statement must hold true. And this is what we're going to be trying to prove in this class. Now, enough said already. Let's cut to the chase and get into the class. Welcome again. This is the mathematical induction problem that we have to solve. Now, the first thing I want you to take note of is that this expression is the operant expression that describes each of these numbers for the position of n, while this expression is the operant expression that describes the summation of these numbers up to the position of n. Now, what I just said will make a bit more sense to you when we begin to solve the problem. The process of mathematical induction, by the way, takes three basic steps. So we take the first step is to prove for when n is equal to 1. That is proof for the first position when n is equal to 1. Then we'll now look for an arbitrary position in the series. We can call that position k. So proof for when n is equal to k. And then we go a step further to add 1 to this k and prove for when n is equal to k plus 1. So these are the steps we take to solve the problem. Now, let's begin to solve this problem. Let's start with when n is equal to 1. So when n is equal to 1, we replace all this n here with 1. So for n equal to 1, we'll have 5 times 1 minus 1. 5 times 1 is 5. 5 minus 1 is 4. So let's try here. When n is equal to 1, here should now be 1 over 2 into 3 plus 5 times 1. Now, 5 times 1 is 5 plus 3 is 8. So half of 8 is 4. So we'll have 4 here. So we have shown that these two expressions can be used to account for the first term. Now, someone might even ask, what if n is equal to 2 or if n is equal to 3? If n is equal to 3, that means we are looking for 1, 2, 3. So we put n into this expression, we should be expecting to get 14. That's n is equal to 3. So we do that. 5 times 3 minus 1, this is 15. 15 minus 1 is 14. Now, what we want to put n into this expression, that's when you understand what I was saying, that if you want to put n into this expression, you should now be looking for the summation of this up to the position of n. That is 4 plus 9 is 13. 13 plus 14 is 27. So if you put n is equal to 3 into this expression, you should be expecting to get 27. Now, let's try it. We put n is equal to 3 here. You have 3 over 2 into 3 plus 5 times 3. Now, 5 times 3 is 15. 15 plus 3 is 18. So I have 3 over 2 times 18. 18 divided by 2 is 9. 3 times 9 is 27. So this expression will tell you what will happen if you are adding numbers up to a certain position. Now, but this is not part of our solution. What we are trying to get is just, so this is our first step, which is this. Now let's do for when n is equal to k. For n is equal to k, so we're now going for the arbitrary position in the series. So if we put n is equal to k into this series, what are we going to get? We are going to bring down this series with k. So we have 4 plus 9 plus 14 plus 19 plus plus. Now n is equal to k. We put k here. We have 5k minus 1. 5k minus 1 is equal to, put k here. We have k over 2, 3 plus 5k. So this one is for when n is equal to k. So we can call this one equation 1. Now, we now go for the third step, which is when n is equal to k plus 1. So if n is equal to k plus 1, for n is equal to k plus 1. So we put n is equal to k plus 1 into this. Now we have 4 plus 9 plus 14 plus 19 plus plus. Now this is the position of k. This is the position of k. Now plus the position of k plus 1. Now this is now 5 into k plus 1 minus 1. This will be equal to k plus 1, which is n, divided by 2, 3 plus 5 into k plus 1. Now this is equation 2. Now at this point now you can see that what you have here, this whole place, this whole region is identical to this whole region, and this is equal to this. So we can just replace this with this, since this is the same thing as this. So to make the work neater, so we have putting equation 1, putting 1 into 2. We now have this, replacing this now, k over 2, 3 plus 5k plus this now, 5 into k plus 1 minus 1 is equal to k plus 1 over 2, 3 plus 5 into k plus 1. So now we can begin to expand. So use k to multiply everything inside this bracket to have 3k, k multiplying this, plus 5k squared over 2 plus 5k plus 5 minus 1 over 1 is equal to, so first of all, expand the one inside the bracket. So we have k plus 1 over 2, 3 plus 5 multiplying k plus 5 multiplying 1. So this is that. Okay, now we can take LCM of this. We take LCM of 2 and 1, we have 2. LCM of 2 and 1 is 2. So if 2 divide 2, we have 1. 1 will multiply everything here now. So we have 3k plus 5k squared plus 1 divide 2, we have 2. So multiply everything here by 2. So 2 multiplying 5k is 10k plus 5 minus 1 is 4. So 2 multiplying 4 is 8. Is equal to, we just want to open this bracket by multiplying through with k. We have 3k. K multiplying this is 3k plus k multiplying 5k is 5k squared plus k multiplying 5 is 5k plus 1 multiplying 3 is 3, multiplying 5k is 5k plus 1 multiplying 5 is 5. over 2. Now I'll move all these things over to this place to complete it. So here we have, so we can arrange this now. Have 5k squared plus, now 3k plus 10k is 13k. So I have 13k plus 8 over 2 is equal to this. We have 5k. So let's put 5k first. 5k squared, sorry. Then we'll have 5k plus 5k plus 3k. That should be 13k plus 3 plus 5. That's 8 over 2. Now you can see that the left hand side is equal to the right hand side. So we have successfully shown that for any position in this series, no matter the arbitrariness of the position, k plus 1, these two expressions can be used to account for them. And this is the answer. Keep solving problems, not away from them. Until next time, bye bye.